So good afternoon. Very sorry that we don't have coffee yet, but this may be even a better tradition. We're going to have refreshments after the seminar, so we might keep our questions short and go get some good. Or you can walk out after the seminar and go get your coffee. Today, it's my great pleasure to introduce Professor George Barbastathis, who is one of my favorite people in all of optics. So I'm honored that he's here except for Professor Messer. um, George graduated from the National Technical University in Athens, and then he joined the California Institute of Technology, and then he was a Beckman Fellow at the Beckman Institute at the University of Illinois before joining the faculty at MIT, where he's a named professor. But what's the name of the professor?
Ralph and Elias Gross.
Okay, I won't say that. But George is a fellow of Optica and SPIE, and is talking to us today about machine learning at the extremes.
Thank you, David. I think I need to put on the... Well, thank you very much for the invitation, and thank you all for coming here. It's really great to be back. I've been at Arizona quite a few times over the thousands of years that I've been around in the profession. So it's always nice to come back to a place that does real optics, right? You know, many of us claim to do optics, but nothing like Arizona and Rochester. So it's very nice to be here. So today I'll be talking about computational imaging, which of course is very prominently featured at the university here. So please keep me honest, right? If I say anything that you disagree, or please speak up. It would be nice to have a debate. So for the last few years, of course, machine learning has become a big deal, and as everybody knows, if you have a degree in AI or something, you're going to make a lot of money. But it is also an influence in our profession, and I'd like to talk a little bit about at least my personal view for what this recent revolution, what it can do for us. So for almost 10 years now, we've been working on similar topics. And what we came to think, we meaning when I say, oh yeah, before I do that, let me say that I also used AI to prepare this talk, and I've started pointing out to audiences this disclosure that I make, that I did use AI, and I take complete responsibility for what I show. I think it's, because sooner or later all of us will be using it. I think it's nice to make a habit of it. Anyway. But go back to what AI can help with imaging as a discipline. We came to think that AI can be helpful if you have extremely challenging situations in an imaging system, such as when it is very dark, meaning you receive very few photons, so in other words, it's very noisy. If you have things that are very small, so due to diffraction limits or pixel sizes, you are undersampled or blurry. And a more recent thing that we have started working on, and I'll tell you a little bit about it at the end, is if you're temporally undersampled. In other words, either the phenomenon is very fast or your detector is very slow, and you have to temporally interpolate. So the last part is unpublished, but I don't mind to tell you what we're doing. It is also in progress, so a lot of things we're sort of still polishing. Okay. So, and of course, when it comes to all of three cases, the way you handle them in general is by regularizing, meaning by using, I'll tell you what a regularizer is in case you don't know. But basically, machine learning allows us to make very good regularizers. That's what it comes down to. So I'll step back a little bit and talk about imaging in general. It is one of the most ancient, undertakings that humans did, starting with pinhole cameras that at least my AI told me that pinhole cameras date back to Archimedes and people like that. And then, of course, there were the old-fashioned cameras, with the dark cloth that the photographer would do, and then the folding Polaroid cameras that I guess even my parents, not your parents wouldn't know, but my parents would remember. and then, of course, mobile phones. And there's been a kind of evolution in how images have been recorded. What you see there is a daguerreotype, one of the first recording ways. It was called a daguerreotype. It is a kind of film, but very primitive, and you see a picture of Abraham Lincoln. And then sort of a few decades later, a family picture. So this picture, this revolutionized many things, not just science, but also society more generally. For example, it made it possible for people to see their leaders, what they look like, right? Before that, they had to go to the White House to see a painting of George Washington. But then, they could see publicly disseminated pictures. It also influences political events, as I guess we're experiencing right now, with some things happening in a state north of here, slightly northeast, I guess. This is a picture from a famous book called War Against War. I don't know how to say that in German. This was published after World War I. And the photographer went to the battlefields and took pictures. And this actually pointed out to people that war is a horrible thing. Up to that point, people thought, oh, war is glorious, and wonderful, but especially World War I, because it was very mechanized. It was very cruel and horrid. So he published this book with pictures, which I don't want to show actually, because many of them are extremely disturbing. And of course, it did not stop World War II, but in any case, it started to open people's eyes. There's another famous picture. It is the assassination of John F. Kennedy. This is also interesting because, as you probably know, it is a controversial event. There's still conspiracy theories around this particular incident. And in this particular picture, if it has been doctored or if it is real or whatever. So it really influences life in many ways, including politics and our society. Going back to science, of course, imaging has had a tremendous impact in a lot of disciplines, including biology and medicine. This is one of the earliest biological images taken by Zernike. It is the origin of the so-called phase contrast method. It won him the Nobel Prize. This is two Nobel Prizes. One was the invention of X-rays, or the discovery rather of X-rays by Röntgen. And that is, it is supposed to be his wife's hand actually, and you can see her wedding band over there. And then the other was the invention of tomography, right, by Hounsfield and, sorry, I forgot the name of the other person who won the Nobel Prize. Very rudimentary, right? But this is also very significant because that's one of the first instances where people started really to use computation. In this case, there's no other way to form an image that a human would understand without computation, right? So that was very significant. And then that is a local product from your colleague, Professor Frieden, who also very early in the, well, as early as old I am, I guess I was born in 71. So he was doing the convolution of images. So this is an example from a crater on the moon that they could see it from the Earth, and of course it would look very blurry. But then Professor Frieden did this the convolution, and then at some point later, a satellite, or no, not a satellite, a spacecraft actually went near this object and took a picture from nearby, and you can see they kind of agree, right? So that gave people confidence that using computation, you can actually retrieve features that were missing from an unprocessed image. Okay, so in all of these computations, as you may know, if, for example, if you've taken Professor Brady's class, the key concept is something called a regularizer, and the way I define it very, very simply is that the reason imaging is difficult is it basically comes down to this, that when you try to recover information from an image, very often the answer is not unique. So you have a single measurement. Think of this now as a whole measurement from your camera, from your sensor, but then there is several possible objects that can fit this measurement. That's what mathematicians call non-uniqueness. And the regularizer is an exclusion principle. It is a mathematical device that allows you to reject ideally all of these except one, right? So now you arrive back at a unique answer. And the way you do it by, if you need some prior knowledge that says, no, this is not acceptable, and until finally you eliminate all of them except one. So that's one case. This situation with multiple solutions is called ill-posed. Another related but not exactly same condition is ill-conditionedness, which means that the solution is unique, but it is very strongly impacted by noise. And once again, the regularizer does the same thing. It keeps the sort of, now the solution is sort of all over the place, but it keeps it to a relatively narrow range. I have a cartoon that I show my students, and it was done actually by AI. It is a unicorn in the city, right? So, okay, we know that unicorns do not exist. So if your imaging system produces a unicorn, most likely it should not be there. So this regularizer would say no unicorns. This unicorn, as you probably realized, it also has another strange feature. It has 5 legs. But I did this many years ago when AI, generative AI, was not that good. So anyway, it kind of makes the point even stronger. Right. So that's why we need regularizers. And of course, this is something that mathematicians have been playing around for a long time, going back even to one of my own colleagues, Professor Norbert Wiener at MIT, who founded a lot of disciplines, including stochastic processes and all of that. But he was worried about this. You know, when you solve inverse problems, how do you regularize? And then another name that I forgot if I have somewhere is Andrei Tikhonov, a Soviet mathematician in the 1960s. And I think the name regularizer actually traces back to him. The more modern ideas go to another mathematician, Ingrid Dobessy, who I think David knows very well, right? Because she used to have I think she still has an appointment at Duke, right? Yeah. And even before, I mean, this paper is from 2004, but even before that, she and the community of so-called functional analysis or harmonic analysis, they were worried about these kinds of problems, and they were using sparsity as a regularizer, basically using things like wavelet decompositions and other such linear transforms. They would try to use these kind of, I'm not going to go into the details of this, but these are sort of various nonlinear iterations that they had come up with. I will come back to this shape. This is called the proximal gradient. And this is the nonlinearity that goes into this iterative scheme. So these are supposed to promote sparsity, and you can use that as a regularizer to eliminate non-sparse solutions. So what Dobessy was doing was using sort of a generic linear transforms. At about the same time, another famous paper is from Cornell, this one. They came up with the idea of using data to discover properties of images that you can use to regularize. In other words, again, to reject improper images. And this came to be known as dictionaries, this idea. It was, again, now going back and using Dobessy's ideas. Oops, I think I bumped something. Oh, yeah. So this another group of mathematicians, this one from the Technion in Israel, they started using Dobessy's ideas of optimization with nonlinear iterants in order to discover what these dictionaries look like. And these are now data driven, right? That's sort of the big deal. Not generic like wavelets, but data driven. In our community, there was actually your own Professor Brady who made us all aware of all this class of mathematical tools with a classic paper on holography, digital holography, where he showed that in a very highly ill-posed situation where you have a longitudinally extended object and you want to use the hologram to extract its depth structure, he saw that you can use one of these compressive priors and the ideas that originated with Dobessy in order to resolve it, right? So you can see these are like 3 or I don't know 2 dandelions, and you can see in the compressive image they are well separated. Whereas if you try to do the standard up to that point digital holography, of course, they cannot be. So that is how we all became aware of all of these tools. And at about the same time, interestingly, the machine learning community, back then, nobody dared to admit they're working on AI. It was kind of like a dirty term, right? But anyway, they were kind of working on it and they realized that the compressive ideas had to do with learning. So this paper is actually probably the most useful thing I will tell you today. Very few people know it. Gregor and Lecun, 2010. They pointed out that the ReLU, the standard nonlinearity that we use in modern neural networks, they pointed out that this allows you to do a kind of a sparse decoder. And again, I'm not going to go into the details of this paper, but there's a beautiful analogy. Remember, I said OSC derived this proximal gradient as a way to sparsify, to produce sparse regularizers. But then you notice that the ReLU, the nonlinearity of the neural network, basically, if you take two of those and you put them next to each other with an inversion, then you get a proximal gradient. So of course, this is kind of hand wavy, but this paper by Lecun kind of makes out the point that this sort of knee shape, this sort of knee shape nonlinearities naturally produce sparsity, and arguably that's also one reason why modern large neural networks like large language models, LLMs, why they work is actually thanks to this nonlinearity that was predicted by another paper about the same time, the one by Gloro. So it's a very interesting analogy, actually, how imaging and learning, they progress together. So this idea from Lecun, later my friend from Switzerland, Michael Unzer, he found a way to use it for tomography. Again, I'm not going to go into the details of this complicated diagram, but it's a nice principled way of regularizing the tomography problem, which is of course very highly ill-posed. And that's from their paper. So here you see ground truth. This, of course, computational, right? It's not from experiments. But in any case, you see the ground truth with a feature here that's supposed to correspond to a tumor. And then there's the standard filtered back projection that most tomographic algorithms use a flavor of that. And then, this is what you get from compressive imaging, sort of the Dobessi style imaging. And this is what you use, this is what you get by using a neural network. And that is what is actually very significant in this is that they reduce the number of projections that they wanted to take into account for getting the image. And that's of course important because the number of projections also is proportional to the exposure that you give to the patient to harmful radiation. So you can see the ratio there, it's about 20 times less dose here, which means you can make the tomographic operation far less dangerous for the patients. To my knowledge, this has not been clinically used, and that is of course because the medical community, for its own good reasons, is extremely conservative. But still, that's a very, very thought-provoking paper, right? That you can pull off something like this. Okay, so this is kind of an introduction to give you the context of what is the things that I'm interested in. And this is a list of things that we've done in my group, and I'll try to walk you through with a little bit of detail on all of those. So the first problem that we got interested in was actually very similar to the Zernike problem. It is called phase imaging. So I'll talk about this first. You may be familiar with it, but just for the sake of completeness, let me point out how we think about this problem. It's very highly applicable to biological imaging. This could be like a biological cell, right? And you can see the nucleus over there is the slightly darker area. So what were we trying to image here? Well, we're imaging the index of refraction, right? Some people call it phase imaging. I don't like the term because nobody really cares about the phase of the optical field. But we do care about the index of refraction that gives us shape information, right? Okay, so that's actually a difficult problem to solve. You need to solve a scattering equation to properly figure out what happens to the electromagnetic field, but under some conditions of smoothness and weakness of the modulation and so on, you can come up with a simple approximation that says, well, I can approximate this as a thin film where the optical thickness controls the phase. That's where the name phase imaging comes from, actually. People conflate the idea that the phase can be proportional to the index of refraction. It is actually what the image. Okay, so that's called thin film approximation, and it saves you from doing a lot of math. But even with this approximation, the imaging problem is hard because the evidence of the shape in your measurement is in the phase, but of course you cannot measure phase, right? We can only measure intensity. So a large body of optics literature actually has to do with this problem, and there's all kinds of techniques that you may be familiar with: holography, tachography, Zernike's phase mask, and so on. The particular technique that we chose to implement when we did this project is called, well, depends on what sub-gang of optics you belong to, coherent diffraction imaging. That's a term that they use in X-rays. And then, so the idea is that it is actually nice because it is lensless. You let the light illuminate the specimen, then you let it diffract in free space, and then what you get is this convolution in the paraxial approximation, and then you get the modulus square. But now, thanks to this convolution, the hidden phase will reveal itself, right? That is the idea of coherent diffraction imaging. And that is also a very, even now we're in a subset of phase imaging techniques within its own subset. It is also a very highly celebrated and worked on method. It started with two fellows, Gershberg and Saxton, also about the same time as I was born. And then, of course, Jim Finnep at the University of Rochester, he really is the one who made it practical because he worked out a regularizer, in fact, that allows you to get this with a relatively good chance of uniqueness. Before that, even Gershberg himself had written a paper that said, "Oh my God, my technique is, ill-posed. I can get multiple solutions." And then Finnep actually solved this problem. Okay, and so what we did is we decided to apply neural network instead of using the Gershberg-Saxton algorithm, which, as some of you know, is iterative. It tries to recover the phase from the Fourier transform modulus. We decided to use a neural net, and so we submitted this paper actually in 2016. And we got a really vile rejection from Optica because they told us, "Why are you doing it?" They said the Gershberg-Saxton works quite well. Why do you bother with a neural net? So we went back and forth, and the truth is we did not know why we're doing it. But anyway, after a lot of blood and sweat, we were able to convince Optica to accept it with the rationale that, well, it's interesting, right? We don't know what it is good for, but it's a new way of doing things. So why do you just let it publish it anyway? So they let us after. And soon, actually, thanks to a project that I had with the government at the time, let me skip that because these were basically the kind of improvement. But we did discover why it may be useful. And the answer is it can be useful if the image is very, very noisy, meaning that you have a low photon count, and then your measurement is severely infected by shot noise and all of that. And then we wrote this paper. This is one of my favorites, GUA 2018, where we showed that now the neural network can indeed regularize this very highly noisy measurement and can allow you to perform the phase retrieval operation or the coherent diffraction imaging, even though the data are extremely noisy. Okay, then we did a sequence of papers improving upon this idea. You can look those up in the literature, but I'll show you in the next slide the progression of the reconstructions, starting with the baseline and then three papers sort of doing more and more sophisticated signal processing. Okay, so let me first of all describe what's happening here. So to demonstrate the idea, we used a special light modulator, a phase SLM, as I was discussing with your colleague. This was actually liquid crystal phase SLM. This is a phase modulation, right? So the color corresponds actually to phase delay, not the brightness. And then this is what the measurement looks like. So this is with an average of 1 photon per pixel incidence. We deliberately attenuated the light in order to make this happen. And then you can see the baseline. This is over the neural network that we had done, the one that we had trouble publishing in Optica. You see it is not doing very well, right? So the Optica reviewers were actually right. This was useless for this particular problem. But then we came up with the idea to combine it with a Gershper-Saxton algorithm as a pre-processor. And by the way, Gershper-Saxton also fails when you apply to this problem. Interestingly, they fail in complementary ways. The neural network gives an extremely low-pass filtered image. Gershper-Saxton gives like a very strongly modulated image. But in any case, when we use this terrible reconstruction as an input to a neural network, then we were able to get this, which is of course not very good, but it does begin to resemble the actual signal. And then, okay, we did like a sequence of other papers where we progressively improved it, and then we could not improve it anymore. So I don't know for sure if we exhausted it. There's some physical fundamental limit that we hit, but anyway, this is the best that we could do. And this is what it looks like. As I said, this sort of the setup. So of course, it's a reflective spatial light modulator, and the light goes into. There's no lenses here, so you get a diffraction pattern on a CMOS. And then this is the Gershper-Saxton algorithm, and this is used for training. So basically, we produce a couple of thousand of phase signals into the SLM. We train it this way in the so-called supervised mode. And then when you use it, of course, there's no more ground truth. So when we use it, the intensity, the diffraction intensity goes into the sequence of Gershper-Saxton and the neural network, and we get a reconstruction. And the neural net that we used back then, it was very popular. It was called the UNet. It was actually, it originated from medical image segmentation. And it became famous because it won some kind of a competition that the machine learning community had about this particular problem. And then it became ubiquitous. It was used very, very. In fact, even now, I think there's a Facebook algorithm. You can download it from the Meta site that allows you to do image segmentation in highly, in rapidly moving scenes. And it is still based on the UNet, as far as I know. Okay, so let me go to the second class of problems. But I've already told you a little bit about this project because I said, we have a very low light, very low photon incidence. What motivated us to look into this problem for coherent diffraction imaging was a project I had at the time with IARPA. I stands for intelligence. Not the artificial intelligence, but the sort of the CIA kind of intelligence. IARPA is a sister agency to the CIA. They report to the DNI, the Director of National Intelligence. So they wanted us to do imaging of integrated circuits, and the problem came because when you image an integrated circuit, it's a very complicated problem. So sometimes you have to do it fast. You have to scan the circuit very fast, and then you get very few photons on the detector. So this is what prompted us to look into the dark situation. And that's exactly what we did for IARPA in the course of the project over like 5 or 6 years. We were able to show that you can speed up the imaging of the integrated circuit. So to give you an idea, you see the reconstruction here without going into the details of how this happened. It was 6 years worth of work, right? And several papers. But to image this is not a full IC. This is like a small segment of it. And it would take the way the national laboratories that we collaborated, the way they were trying to do it, it would take 3 full days for this tiny portion. This is a few cubic, a few hundreds of cubic micrometers. That's how big it is. It would take them 3 days to finish this operation. And then by using machine learning, we reduced this by a factor of about 100, which means a little bit like 3/4 of an hour. That's of course huge savings. I'm not going to go into that because I'm running a little bit short on time. But a lot of funny things happened along the course of this project. One was the pandemic, which was not very funny. But we started using a class of techniques that at the time was very fashionable. They were called transformers. And the transformers are based on the concept of attention. Now, I think all of you use LLMs, including me. And attention is what allows the language model to stay, no pun intended, to stay focused on a particular topic when you talk to it, right? And they're very good at it, actually, surprisingly good, better than me. I tend to digress. So the way they do it is with, they call it an attention mechanism. It is actually the concept comes from thermodynamics. Those of you who know statistical mechanics recognize this expression. It is used it is basically the probability of occupancy of a particular state in a large system. So they use this kind of math to pinpoint, so to speak, what is useful in a sentence when you speak, when you chat with a tool. And then that's how it keeps context, right? Because it has these hotspots of contextual importance. So we use the similar concept for tomography in order to find hotspots of scattering from the object. But this is not really the physical I mean, of course, it depends on the physical scattering. But what it really is the physical scattering that the algorithm decided is important for it in order to reconstruct the shape. So this algorithm actually has been trained by integrated circuits. We had a database of circuits, and then we fed it in supervised mode. So it basically learned what typical circuits look like. The circuit that we reconstruct, of course, in the tests, it has never seen before, right? It is, of course, forbidden to use something that you use for training. But nevertheless, there is something that I will call IC-ness, right? You know, what does it mean to be an integrated circuit? That's what it has learned. And the attention mechanism now allows it to discover which parts of the scattered field are important for the IC-ness property, right? So this is what it learned. So it was kind of fun. And of course, then they're not called transformers anymore. They have different names. They're called foundation models, and there's all kinds of more. This was 6 or 7 years ago, but this is eons, you know, in this very rapidly moving field. So it has evolved a lot. But in any case, that's quite interesting that we use this in a completely different context. Okay, so how much do I have? Another 20 minutes?
No, you still got another, like 30, no, like 20, 25 minutes.
Oh, okay, great. So I'd like to tell you a little bit of detail about that, because even though it is getting kind of old, it's still one of my favorites of the last few years. So that project was funded by a pharmaceutical company called Takeda, and it has to do with the last stages of manufacturing drugs, pharmaceuticals. So believe it or not, this looks like cooking, right? The way you might make a mayonnaise or something like that. But this is actually a drug powder. In one of the final steps, it is still wet with solvents, you know, from the previous stages of processing, and they're trying to dry it. So after they finish this, the next step is they put it in a pill, right? And they send it to the patients. But the danger here is you can see it's a very messy process. It has it's called an agitator, believe it or not. So it has this agitator, and it is being heated. So just like when you make mayonnaise, if any of you have tried, there's a risk of curdling, right? You know, it can agglomerate, and then of course it will be destroyed. You have to throw it away. But here, if that happens, the damage is far worse. Because, okay, first of all, why it is important here? Because the FDA has very strong restrictions on the uniformity of this, obviously, right? Because if you send pills that have non-uniform dose, some patients may overdose, and for some others, there's not going to be any effect at all, right? Now, if it fails, you might say, well, they have to throw away the product, which is already a loss because these are expensive. But it's even worse, because if the process fails, the FDA will force them to shut down this particular reactor until the FDA gets around to send an inspector that it is okay again. So they can be weeks or months. So they lose tens of billions of dollars if the process fails. It's a very important problem for them. And as you say, it's in completely human intelligence is solving it. They literally employ people, just like you see this person over there, to stand on top of the reactor and look through. There's an optical window and monitor it. And so we talk to them. So you say, what? How do you know if it is agglomerated? They say, well, it's a gut feeling, right? The sample development. Anyway, so they came to us and they asked us to automate it. So, one obvious way to do it is again to use supervised learning, and that's exactly, in fact, that's what they wanted us to do. They have thousands of these videos, and they wanted us to train a neural network from these videos. But we had been, when they came to us, we had already been doing that stuff for years, right? So we're kind of bored. I didn't want to do even more of this kind of thing. So I came up with this alternative, which looks at first even worse. The alternative is to illuminate it with speckle, to illuminate the surface with, well, to illuminate it with a laser beam, and then you pick up the speckle that is backscattered. So that was my idea, and then I gave it to my student, Zhang Zihang, and I told him, well, okay, just do it. And we had no idea how to do it. But luckily, he came up with a way to solve it in a very elegant way. And what is elegant is that not only it discovers if the process has been agglomerating, but it gives you actually a histogram of particle sizes. So this is of course a cartoon. I will show you real data in a minute. But just so we know what I'm talking about, the horizontal axis is radius or diameter, and you can see the scale is between 1/10 of a millimeter to a couple of millimeters. This is how these powders are at this particular stage. And then the vertical axis is population, right? So it is even better because, for example, if the FDA has approved this population, then, and this is what you measure, it is okay. Whereas if the measurement comes out like this, it means it has started to agglomerate, right? Because the particles are, on average, they're getting bigger. So that's the idea. Now, there's a commercial instrument that can do this, that can produce this size distribution, but it is invasive. They have to scoop some of the product and put it into the instrument. And it's also slow. It takes about 50 minutes to do the measurement. So, of course, the reactor cannot stop. It has to keep working while they're doing the measurement. So it is not an ideal situation at all. Also, it's a little bit funny, PSD. PSD to some of us means something totally different. It means power spectral density, right? But this project was with collaboration with some of my colleagues from chemical engineering at MIT. And we had a collision there, we had a nice dinner where, we argued about it, and we decided to yield to the chemical engineers and use PSD in their sets as particle size distribution. Interestingly, the power spectral density also comes into this project because we solved it using autocorrelations. But anyway, sometimes you lose these nomenclature fights, right? Okay, so this is how it works. Now this is a calibration experiment. So you see 4 containers, the particles are very well calibrated in each container. You see the size, the nominal sizes in the caption. And then this is the instrument in real time producing its own estimate of the PSD, the particle size distribution. And in between, you're going to see spikes, which happen when the light beam crosses the divider between the containers. So that's a kind of a nice demonstration that the idea is valid. And this is the proof that it can work in real time. Okay, so this is a little bit complicated. So this is an experiment that we ran for over a course of almost 1 hour and a half, 80 minutes. And now here the vertical axis is time. Each one of these rows here is actually a histogram, and it is color coded, right? So you see the color code here. So each one of those is like a hub, right? And you can see the evolution of the hub during the course of the steering. We actually built our own agitator, so we have control. Okay, and these are now 4 sort of selected instances of this process. One of them is at the beginning, so this is the red curve, and this has the nominal sizes. Oh, and here also you can see superimposed the data from the commercial tool. The commercial tool is the master-sizer. It is a sort of a smooth curve because I guess the tool does some kind of function fitting. We don't know exactly how the tool operates, but it gives these smooth curves. Ours, of course, is more noisy, and that's for a number of reasons, including ill-posedness. This is a very highly ill-posed measurement. Anyway, so as the process progresses about half an hour, 25 minutes later, you see it shifts to the right, which means exactly that it has started to agglomerate. And it is visible in the data. And at this point, the students poured some solvent, so the agglomerates begin to separate. And then it shifted back, so you see the green curve about an hour into the process, it has shifted back to normal. And then very late, near the end of the process, you see it has shifted to the left now, means the particles are becoming smaller on average. And that is also undesirable, it's called attrition. This actually happens if they become too dry, and then due to friction, while you stir, due to friction, they might actually start to crack. And that's also undesirable. But in any case, this sort of illustrates. Now, my colleagues in chemical engineering, they love this plot because this process, it is not very easy to characterize using first principles. I mean, you can use the usual stuff. You can use momentum conservation, energy conservation, but the friction, adhesion, and all of these other complicated fluid mechanic processes that happen in there are very, very difficult to model, very difficult to write constitutive equations. So there is hope, I guess, using this kind of plots that you can actually discover the physics of how these processes work. So we're still working on it together with my friends in chemical and the company. So okay, so let me go a little bit faster so I don't run out of time. This is how it works. I haven't told you yet how we do it. So it's actually a pretty simple idea. We take a few, not too many, a few frames of the speckle, and we form the autocorrelation function of this. It's a random process, right? But it's an intensity of autocorrelation, right? Because of course the speckle is intense. And it turns out that if you omit for now this modulus square, if you open Goodman's book on speckle or Goodman's classical papers from the 70s on speckle, this is the formula that you would discover from the autocorrelation of speckle. And it is limited, as some of you may know, it is limited by the pupil of the optical system. So if you have a circular pupil, the speckle looks like a jink, the autocorrelation looks like a jink. Actually, for simplicity, this formula is one-dimensional, so that's why it looks like a sink. But Goodman assumes that this is the autocorrelation of the detector, but Goodman assumes that the autocorrelation of the wave function on the specimen is a delta function, meaning that the granularity is smaller than the wavelength, right? That's how he derived this formula. What my student did is he dropped this assumption and he allowed the particles to be bigger because, as I told you, these are like 10th of a millimeter, much, much bigger than wavelength, right? So, and that's not easy to do, but he did it somehow. And he came up with a really simple formula for the autocorrelation. It is basically a correction over Goodman's or the classical formula, which includes the PSD, the particle size distribution. So this is now the inverse problem that we're solving. This is our indirect measurement after the autocorrelation. And the inverse problem is how to extract P of R out of this mess. That's what we did. Okay. And this is also one of my favorite plots from one of my favorite papers. I forgot to say one more thing. So what does this formula do? So this formula actually dampens the side lobes of the speckle. So what you see here is this formula in calculation and experiment. So the calculation is the bottom part, the top is the experiment. You see they agree quite well. Of course, the experiment has lower contrast for a number of reasons. And but now you see we're going from smaller to bigger particles progressively as you go in this sequence. And you can see that as the particles get bigger, the side lobes become less and less visible. And that's not surprising. This is exactly what the formula predicts. So basically the measurement, another way to think about it, instead of extracting this from the formula I said before, another way to think about it is how can you are an algorithm, how can you interpret the visibility of the side lobes and convert it into this probability density function? And so here you see what the machine learning algorithm is doing. So you see in the background, again, this is a progression from smaller to bigger particles. And then sort of the fuzzy looking diagram is the theoretical calculation for the autocorrelation for the different cases. And then the flame looking things are actually the activation patterns in the neural network itself. This is a special algorithm that allows you to do that. It's called GradCam. It is based on derivatives. And you can see that they kind of match what the theory predicts. As you go to bigger sizes, the flames begin to decay, so to speak. And that's sort of indication that the algorithm here has picked up the physics from its training process. Okay, I could tell you more details, but I'll try to finish first, and I'll be happy to say more about this project later. I want to go to the last thing that we're working on now and sort of polish in a couple of manuscripts, and that is temporal undersampling. Okay, I say this is new, but this is new to me. It is not new to Professor Brady. In 2013, he wrote a paper doing exactly that, but that was kind of pre-machine learning, right? So this paper is using compressive priors to solve basically the same problem. So you see here a video of relatively few frames, and then here you see interpolation basically between the frames. And this is done by a coded aperture, which is a way to modulate the signal, and then by using, as I said, compressive priors, which basically mean that if you had a high-speed camera, you really would not need all this high-speed frame information, because the degrees of freedom in this particular experiment are actually less than you would think if you counted all the pixels from the frames. So this is what allows you to reconstruct correctly in between frames. Okay, so now if you forward again another 12 years or so, this is what well, the new stuff, so to speak, that sort of builds up on David's older work, is that what we're trying to do, what we did in this paper, I will not go into the details of this, but also in the more recent work, what we did is we started using the dynamics of the movement as a regularizer. So in this case, it is a simple continuity. This is a tracking of some fluorescent molecules using the spectrum. So this is a nice paper, but it's using something very simple idea. It is using it basically the regularizer says that this trajectory has to be differentiable. It really comes down to that, and this allows you to denoise it and do the proper interpolation. Let me skip that. But what we're doing now, and I think is far more interesting, is we're using the dynamics itself. We're using the differential equation governing a particular dynamical system. We're using it as a regularizer. So let me tell you first of all the problem. The problem is a MEMS device, micro electromechanical system device, which has a very small amplitude of motion. And moreover, I mean, we're using a synchrotron to image this, and the device is not particularly sensitive to the radiation, so we could get as many photons as we wanted. But in order to make it even more interesting, once again we attenuate the radiation, so now we get very low photon incidence, very noisy images. And to give you an idea, this corresponds. The previous experiment I showed at the beginning was a single pixel per frame. Sorry, single photon per pixel per frame. Here it is 0.015 photons per pixel per frame. So it is extremely dark. Okay, so this is what you get if you have a sort of normal illumination, a lot of light, a lot of X-rays, and this, of course, the diffraction pattern that you get from the structures over here. And this is what you get when you attenuate it. Actually, I misspoke. I think the left one yeah, sorry, this is actually a calculation, not an experiment. This is and this is also a calculation, okay? But the experiments really look like that. Okay, so the way we solve this problem, and I think that makes it very interesting, is that we solve an optimization problem where we penalize simultaneously two terms. One of them is a, so to speak, mechanical term, we call it a K term, and this really penalizes deviations of the observation from the differential equation that governs this oscillator. And the second is an optical term, which penalizes deviations of the measurement from the forward model of light propagation from the specimen to the X-ray camera. And so that is the basic idea. And we solve it really using these quadratic terms, but of course one could employ other techniques such as adversarial in order to do it better. I'll give you an idea what they look like. This is the set of differential equations that govern it. It's actually thermally actuated. So there is thermal terms here, thermal conductivity terms, and all kinds of other weird stuff. And then this is the model of the oscillator. Some of you will recognize it because it has a cubic term. It is called a Duffin model. So, okay, that's what we assume. It doesn't have to be like this. It could be a finite element model. As long as it is differentiable, and finite element models are, then you can use any model you want there. This is particularly simple, so we're using it as a test case. And then these equations are probably even more familiar to you. This is something called coherent mode decomposition, because the synchrotron is, of course, partially coherent. And then this is a propagation equation that describes the free space propagation of the partially coherent beam. And then finally, this is the model of the measurement. This is the intensity term, and then the superposition of modes. Okay, it looks a little bit complicated, and perhaps our notation is making it worse, but this is what it is. So now you have these two models, and the model and the measurement has to meet them simultaneously. And then you can think of it as a data fitting problem. In fact, there's no machine learning here. It's just parameter fitting on these equations. So one thing you can do, for example, is you can recover the mode structure of the synchrotron, and you can do that easily in the high dose case, because then you have plenty of photons. Then basically it is no problem to extract the shape of the oscillator from the measurements. But then the shape will look weird because of the superposition of the synchrotron modes. But then you can see that when you fit the coherent mode decomposition into this complicated measurement, then you can recover something that looks like the modes of the synchrotron. And then this is actually from an experiment, and so let me explain here. So the green curve is a theoretical model which now uses finite elements. It's no longer the Duffin oscillator. And then you see the reconstructions for high dose and low dose. These are the blue and the red curves. And you can see there's a discrepancy. As you can see, the experimental curves have a sort of a low, slow exponential decay, which actually was interesting. I mean, it puzzled our colleagues who make the oscillator, who are proper mechanical engineers. So when we told them this is happening, first they said it's wrong, there's something wrong. Then we said no, and then they said they said maybe someone used an exponential decay in the function generator that controlled the experiment. But turns out it's none of that. It is actually real. It is heat dissipation from the substrate. You know, the oscillator is sort of hanging by a huge chunk of silicon that has its own thermal capacitance, and that sort of creates this decay. So that's very interesting because our model revealed an error in the physics of our colleagues who did this particular design. And by the way, the reason they got this wrong, because in the finite element models, they did not include this thermal capacitance term. The finite element model assumed that this is surrounded by thermal bath, so there's no dissipation. So it's kind of interesting, and this is where we are now. So I think actually This is a cartoon that a mathematician friend of mine pointed to me. He didn't make it, he just pointed it to me. Let you read it. It says, this is your machine learning system. Yep, you put the data into this big pile of linear algebra, then collect the others on the other side. What if the others are wrong? Well, it says then keep stirring until it looks better. So I'm sorry to say that many machine vision or AI algorithms they have this feature. I hope I convinced you that what we're doing is a little bit better than that, right? Nothing is perfect when you do metrology or precision measurements. It's very difficult to establish what the algorithm is doing. But I hope convince you we're doing it better. If I have a couple of more minutes, let me point out that I think this is why the Nobel Prize went to physics and chemistry. Went to AI a couple of years ago. I think I cannot speak for the Nobel Committee, but I think they were making the case that first of all, many of these algorithms originated from physics. The original people, Hopfield, Hinton, some other big names, they're all physicists, right? And they used what they knew mostly from statistical mechanics. They used it as inspiration to design these algorithms. And now it's kind of paying back because a lot of these algorithms are helping physicists to solve complicated physics problems, right? I mean, I showed you sort of the little thing that interests me, but people use it in particle physics, anomaly detection, all of these kinds of things. And yeah, and this is of course the chemistry prize for the protein problem. I like to show this this picture. This is from a Thai television show, and it is about it's about a future, well, a dystopian society where AI is used to establish if you are pious. Of course, Thai people are Buddhist. So if you are good with, and actually, I don't know if anybody here speaks Thai. Buddha in Thai is Sas Data, and of course, that Ta is kind of sounds almost like data, right? So this is the word play in this show, and so basically, AI is beginning to influence all aspects of our lives, right? So I think the time won't be very far when a lot of physical, I mean, up to now it's mostly abstract, right? It's mostly discussion. You can talk to it and it can do maybe collision detection if it is autonomous driving. But I think very soon it's going to start influencing physical things that surround us, kind of like these things that are flying next to this person, maybe it will become physical, right? And I think we're doing something very wrong. All my colleagues who do AI, they try to think of it as a human. We make the same mistake in image interpretation. We try to think that the AI has to see some spatial features in order to interpret them, but it doesn't have to, right? We have to see them because this is how our brains evolve. But AI doesn't have to. And I think one of the interesting things that sort of common theme in everything I showed is that actually the machines they can operate on interesting what do you call it, reinterpretations of the data, like correlation functions, Gershon-Saxton algorithms, and so on, that the human brain cannot really do, but it turns out to be extremely productive for the AI, right? So it is not really image focused anymore. It is more like interpretation focused. So when it comes to this particular case, yes, it is very easy now. These things exist. You see robots everywhere, including at the airport, and here on campus I saw robots walking about. But I don't think that's interesting for robots because when it comes to if someone needs to bring a patient their drink, I don't think a robot is particularly helpful for that. In fact, the patient most likely likes human contact, right? But what a robot should be doing, in my opinion, and this is not really my topic of work, but I'd like you to leave you with this idea. What a robot should really be doing is the sort of the difficult, disgusting tasks that are still done by humans. So, for example, if a patient is incontinent, the robot will bring them their drink, but the really difficult job is how to clean them, right? And how to sterilize them and so on. The robots cannot do it. It's still the humans doing it, right? And arguably the robots cannot do it because the people who make those robots they try to make them look like humans. Whereas, for example, when it comes to a patient, most likely it is the bed that has to do these functions, right? For cleaning and massaging the patient and so on. So again, this is not really the topic of my main talk, but at the end, I would like to provoke your thoughts. And also, of course, a lot of interest in imaging and sensing problems come here, right? If you really wanted to design a device to take care of old people. I would like to provoke your thoughts on this idea that how do we use physics and how we use mathematical principles and physical principles, signal processing and so on. How can you use them to design algorithms that cleverly, intelligently interact with the physical world? Okay, I think I've run over time. Thank you very much.
Yes, so questions?
I think that
I think it was slide 28 where you were talking about IC-ness. I'm a little bit curious for your thing on this because up until the final sort of experiments you're talking about, at each point it seemed as though the sort of final outcome was, well, we got the outcome we wanted from our system, so we know it's good. And the final one, you actually predict some sort of rationale, which is this thermal dissipation of silicon. But for things like predicting IC-ness, what are the actual physical features that are IC-ness in this case? What is your approach actually allow you to pull out as information? And if I go to an IC manufacturer and I then say change these three little features, will that IC, if it's thrown through this system, suddenly be interpreted as like, oh, that's not an IC at all?
Yeah, okay. You asked me two questions. One is very easy, the other is very difficult. The first question, what does IC-ness mean? For one thing, the most prominent is Manhattan geometry, right? ICs tend to be rectangular, right? Rectangular feature. It does not recognize circuitry, or it's not supposed to in any case. It's not like it will find, oh, this is a multiplication or whatever. And there's other things too, right? Which I cannot really articulate anymore, but the geometry is the prominent issue. The second question you're asking me is really goes to the heart of the problem, right? Which is, but maybe I should tell you a little bit more what IARPA was interested in here. They were interested in ICs that may have deviations from the design, right? Someone, for example, inserted a piece of circuitry that was not supposed to be in there. So that actually problem we didn't get to solve because by the time the project stopped, they told us, thank you very much. And then we said, oh, we'd like to work on it more. They said, oh, no. They said, we'll take it from here. So I don't know what happened. Remember, this is the IARPA, right? But okay, if I had continued working on it, I think this would be the most difficult question, right? Can you establish a confidence bound that tells you, oh, yes, this is really a valid IC versus no. And there is a way to do it. There is ways to do it, probabilistic maximum likelihood techniques and but it's very, very computationally expensive, right? And it's a really difficult problem. And there's always going to be some uncertainty, right? That's the best I can say. Yeah.
Showed us a picture of Abraham Lincoln, probably from the 1840s or early 50s, said that's what the technology allowed us to see our leader. My question for you is there a technology today that allows us to not see the leader?
Depends on the leader. But you're also right. I mean, the unicorn is also, I think, is making the same point, which is that now we can alter images with almost no evidence or very little evidence, right? So there's a question: what is reality? Is it what we see? Yeah, that's also a very difficult problem. I'm not really working on it, but the regularizers have the potential to ameliorate some of these questions, right? Because I think generative models, they're getting better, but they can still miss some of the physical details very subtly, right? So there's still a way to detect them. I think there's a question back here.
But it's more like an open-ended question, but can you maybe comment a little bit on the importance of baking physics into your AI? For example, in your favorite project, right? You calculated the autocorrelation of the speckle pattern, and this was then the input to your network, right? So you could have also just taken the speckle pattern and let the network find out the autocorrelation by itself, but this would probably not be so successful. So
Yeah, actually,
comment a little bit on that.
Yeah, thanks for reminding me of that. There's something I should have said and I didn't, so thank you for giving me the opportunity. Actually, you could have done that, but it would require a lot of data. And this is expensive to acquire data. I mean, this whole project actually rested on 24 data sets. We had 25 powders with different size distributions. We fed them into the commercial tool, blah, 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 right? So it's not like face recognition. You know why face recognition works, for those of you who are young? I remember when I was a grad student 30 years ago, most of my friends, they were trying to solve face recognition. You know where they couldn't solve it? They did not have enough faces, right? Every lab in those days, they would get all the grad students, they would take like 20 pictures, like 50 pictures, that was it. Then Facebook came along. Again, you're probably too young even for Facebook. I remember when Facebook was issued. And then suddenly people would go in and post the pictures of their friends and label them, right? We don't do that anymore, but back then you would go and tag your friends. Now Facebook has its data set, right? You know, millions, suddenly millions of pictures tagged, presumably correctly, right, by users for free. Nobody even paid those users, right? So that's why face recognition works. But we don't have this luxury in physical systems, right? So one really good practical reason is because it's very expensive to collect data. There's also a philosophical reason which says that physics rests on logic, right? You know, momentum conservation, as far as we know, has not been violated. So yeah, it's a nice guardrail, because if your algorithm learns from data but somewhat violates momentum conservation, something is wrong. That's also a good reason, yeah. So I really believe in it, even though when I talk to my colleagues in the computer science side of campus, they jump at me.
Because like originally there was this like thinking about, which was basically the cartoon that you showed at the end, right? So I have a big pile of stuff and I just throw stuff in and see what comes out, right? But yeah.
In some cases, you don't have a choice, right? For example, with language, you really don't have a choice. You just have a pile of stuff. But with physics, you can do better, right? So why not do better? Yeah. Thanks for the question. I think there was one question here. Or,
Yeah.
yeah.
And
then you.
Is it fair to say that the theme of your all the regularizers that you implement is differentiability?
Yes and no. I mean, differentiability goes also to the forward model, right? I mean, it's basically how you do parameter estimation. The regularizer is more like guiding the parameter estimation away from places it shouldn't go, right? And actually, some of these regularizers are not differentiable, so you have to do other tricks. That's where the proximal grading actually comes from. It comes from the fact that the sparse regularizer is not differentiable. Did they make any sense? Or?
Yeah, it seems they still do a gradient descent on ReLUs, right? So I'm talking about alternatives that you can't do gradient descent. Some sort of like a Markov gradient.
Yeah, I mean, and now again we're veering a little bit away from my everyday. But to answer your original question, differentiability is not tied up to the regularization principle, right? The regularizer is there because you need it for some other reason, and then of course if you can do gradient easily, it's fine, right? The ReLU is very nice because if its gradient is either 1 or 0, right? What happens at that little non-differentiable point? We're engineers, right? Let's not worry about it. But that's fine, you know, it works. I think yes.
Do you have any thoughts on a lot of your work was supervised machine learning models? Thought about using unsupervised learning?
Yeah, we have. We tried it some projects that I didn't mention because they were not very successful. But actually, unsupervised learning is the underlying principle of all these regularizers. Going back to the previous question, how do you discover a sparse representation? Well, unsupervised learning will do it, right? And in fact, dictionaries are one unsupervised learning algorithm. So it's there, right? Except it didn't come up prominent in any of these projects. We try to do it with biological cells. We try to see if we use coherent diffraction, and then if we try to use the shapes established with some other way, can you really cluster them? And that was for a particular type of immune cells. I think they're called CD8 and CD4. I forget the details now. That did not work for some reason. So I guess it left a little bit of a bitter taste. But it doesn't mean it doesn't work. Maybe we just did something wrong. Yes.
The machine learning process and kind of your output data that will allow you to better sense your data, use kind of a different method. So for instance, for the powder kind of analysis versus, looking at the video versus looking at, speckled data from it.
Yeah, that's also a difficult question. Well, okay, I think the closest I can point to you to is this. Hopefully, I can bring it back up. This picture over here, where you can see the two algorithms failing in a different way, right? I mean, the Gershwin-Saxton FinUp is regularized and it fails in this grainy way, and the neural network fails as a low-pass filter. But thank you for asking the question. I mean, I'll have to think about it more deeply. Like, is there more general conclusions one can draw, perhaps? I think actually, especially when it comes to failures, that's a very good question to ask, right? Because if it works, I mean, when you go to the boundaries where it might stop working, it would be good to have a definitive answer to your question, right? We don't have it right now, but it's a good direction. Yeah, thanks for that.
Thanks, George. Get out and have some coffee and pizza. We have this wonderful
Oh.
gift for you.
Oh, thank you very much. Yeah, very nice.
Thanks again.
Thank you for inviting me.